This is the first video on Chapter 15, Limits. So we're going to be looking at the limit as x approaches c of f of x is equal to L. And so one of the harder definitions in calculus is the epsilon delta definition of limit. So I've drawn a picture here to explain the epsilon delta definition of limit. I'm going to do an example to illustrate that. I will do several examples from this chapter. But this is the first video. And so first of all, we have this definition. So definition 121, I did not write it out in all of its detail in the video since you have your notes in front of you. But it says that if x is in the interval c minus delta to c plus delta, but without c, that implies that f of x is in the interval L minus epsilon to L plus epsilon. And another way to say that is that if the distance between x and c is less than delta, but greater than 0, then the distance between f of x and L is less than epsilon. And so I've drawn a picture here to illustrate this. First of all, the function value f of c is up here. So, and the limit is L. So the limit and the function value do not have to be the same, and in this picture they're not. They're allowed to be the same, but they don't have to be. So I've drawn them separately here to illustrate the fact that the limit and the function value do not have to be the same thing. And so what's happening is we have this L minus epsilon to L plus epsilon, so we're looking at all the points with an epsilon of L. And we want to get our function values in this band right here. So we're going to get our function values right here. How do we do that? By getting x in this interval, not including the c. So if x is here or here, where is f of x? Well, it's between here and here, so it is within L minus epsilon to L plus epsilon. So this is the picture of the epsilon delta definition of limit. Now this part here should remind you of the assignment 1, where I gave you some assignments using the absolute value. What I was doing was giving you some exercises that were similar to what you're doing in the epsilon delta definition of limit. We have the limit as x approaches 5 of 3x minus 1 is equal to 14. I will point out that in this particular case, the limit and the function value are the same. If you simply substitute 5 for x, you get 14. So the point that I was making in the picture isn't that the limit and the function value are never allowed to be the same thing. It's just that they don't have to be. What example 123 asks us is, how close to 5 does x have to be in order for 3x minus 1 to be close to 14? And what do we mean by close? We mean that the distance between 3x minus 1 and 14 is less than epsilon. Remember, absolute value is how we measure distance in the real line. Well, this inequality is true if and only if this inequality is true. So we simply added negative 1 to negative 14 to get the negative 15. This inequality is true if and only if this inequality is true. We simply factored out a 3. Factored a 3 out of the absolute value because we can do that. The absolute value of the product is a product of the absolute values. So this inequality is true if and only if this inequality is true. Divide both sides by positive 3. That preserves the inequality. So this inequality is true if and only if this inequality is true. And so because these are if and only if statements, x minus 5 is less than epsilon over 3 if and only if the absolute value of 3x minus 1 minus 14 is less than epsilon. So we set delta equal to epsilon over 3.